Hello, everyone. Thank you for joining us for today's webinar. My name is Kaylin Shores, and I'll be moderating today's presentation on EMA3D Cable 2021 R2 Electronics and Consumer Electronics. Before we start the presentation, let's review the user interface. The large window in the upper left is the primary window for today's webinar. You should be seeing the title slide right now. To the right of that, you'll find the Q&A window. If you click the arrow next to Q&A, you will see a field at the bottom of the screen where you can submit questions. At any time during the presentation, you can submit your question. Your question will be placed in the queue and will be addressed at the end of the presentation. Any questions left unanswered will be responded to via email. Okay, on to today's speaker. Tim McDonald is the president of Electromagnetic Applications, where he has implemented new system modeling approaches to simulate the interaction of systems and their electronics with electromagnetic environments in a shorter time, with more accuracy, and at a lower cost. He is a consultant to NASA and DoD major primes for specialty engineering of critical systems, development of novel material solutions to EMI and EMC problems, and in the execution of major programs that require verification to electromagnetic environmental effects. Without further delay, I will pass it off to Tim to get us started.
Thank you very much, Kaylin. I'm happy to talk today about EMA3D Cable. This is the new release coming out on July 7th, and it is referred to as 2021 R2. So EMA3D Cable is a unit-level electromagnetic modeling solution. And so EMA3D Cable is a full-wave simulation tool with special features for modeling wires. EMA3D, its interface is integrated within the ANSYS SpaceClaim platform, which gives users the ability to import CAD, run simulations, prepare the models, post-process the results, and make plots and animations like you see here. ANSYS EMA3D Cable is available through the ANSYS sales channel, so if you're interested, talk to an ANSYS representative or one of their channel partners. The main things that I'm going to be talking about today for ANSYS EMA3D Cable are going to affect users specifically in EMI EMC today. The reasons to use ANSYS EMA3D Cable maybe over another tool are with respect to its accuracy and its ease of use. So EMA3D Cable is actually an old solver. So for more than 30 years, EMA has been developing the wire modeling tool and the 3D FDTD tool that compose EMA3D Cable. And over that span of time, there's been more validations with these solvers on large platforms than any other tool in this domain. So it's a full wave solution of the electromagnetic equation, so it can be applied to a really wide spectrum of problems. We're going to be focusing mostly on EMI EMC problems today. And the 3D solver in FDT is fully integrated with the wire solver. The tool is easy to use. The user interfaces within ANSYS SpaceClaim, as I mentioned. It's a very intuitive tool for new users. With an hour or two training, new users can start to be productive on simple models. Expert users can prepare models of full vehicles or full units, enclosures, and their cables in a much shorter period of time than other tools. And it's really that workflow that is the reason that you would want to pick EMA3D Cable. It's going to take less time to put the models together and then less time to run the simulation. The workflow is integrated with the ability to pull fields in from ANSYS SIwave or ANSYS HFSS. Why would we want to do EMC simulation? EMC lab test is typically the method of compliance. However, by the time you finish your unit or you finish your vehicle, it's really expensive to make changes. If you're able to predict the performance of the units or the vehicles early in a program, you can save cost on redesign. In the past, the problem has been it's really hard to include these enclosure and the cable effects, whereas most tools focus on good PCB design and good EMI EMC practices. For the enclosures and cables, you just followed rules of thumb and good luck in the actual test. With EMA3D Cable, we start to have the ability to predict some of those unit level effects. So of course, there is a big schedule risk, and cost benefit to making changes. Traditionally in EMC, with respect to the enclosures and cables, the old paradigm is to build it, then test it, a physical prototype. And if you have to redesign, it's later in the development cycle, so it's much more costly. However, if we can predict our performance and anticipate some of the design challenges, we can make those changes much earlier in the process and cut our overall development program cost. Now, enclosures and cables are complicated. So we've had for a long time a collection of really great tools for simulating PCB emissions and other criteria with respect to EMI/EMC. But as you know, that cable coupling is heavily impacted by the cables and the enclosure. For radiated emissions in particular, shields or lack thereof, and the termination of those shields, whether it's a pigtail versus a 360 termination, whether the shield is grounded on both sides, those have big impacts on the emissions. Enclosures can have apertures for fans or venting, or other apertures. There's seams and joints at the lids. There may or may not be gaskets there. And then we have some exotic materials like EMI absorbing tapes, or it may have chokes on our cables. All of those things that we know heavily impact EMI/EMC. So why wouldn't a team want to consider those effects earlier in their program? It's time consuming to build the model with previous methods. It can just take a really long time to put all the complex details of cables in the enclosure, and it may not be a computationally efficient solution when you're done. Well, for those concerns, the solution is the EMA3D cable. The workflow that I'm going to be talking through today is much easier to put together. Instead of talking about weeks of time for an enclosure model, you can import the MCAD, mesh it with the EMA3D voxel style mesh, and you can be simulating in the same day. And then the same way for the cables, we have the ability to import the routing of cables, import details about the cable cross-section from wiring databases, and be running in the same day instead of a week's development program. So it's really that workflow that is a game changer for EMI/EMC in simulation. It opens up simulation to much more complex systems. Okay, I'm going to go through several concrete examples today. The first one we're going to look at is electrostatic discharge in cables. So with consumer devices or non-consumer electronic devices, there's many ways we can have a discharge. One of the biggest threats is just human ESD, where I'm charged up and I touch a touch screen on my car dashboard and I get a little shock. That ESD is something that is maybe considered safety critical, maybe really important to pass your EMI/EMC. So let's talk about ESD, and in particular today we're going to be talking about conducted ESD that's forced to flow on a cable. So in this case we've got our ESD happening on the monitor, and the monitor itself is not necessarily grounded, and there's a data cable that connects the monitor to the CPU device, and that CPU device is grounded. So when I discharge my finger to the computer, the only path for the current is to go flow along the cable itself. So EMA3D cable, true to its name, is a very straightforward tool to model the cable effects. So let's start with the ESD source signal. So there's a predefined library of signals, but we can also pull in the signal file from an ASCII. And in this case, we're looking at the ISO standard ESD waveform. And then we're seeing the 3D simulation. You can see the staircasing effects of the EMA3D voxel style computational mesh. And you can see the current, the only path for the current is to go between the CPU and the monitor. And we can add some varying details of our cable termination and the cable itself and see how that affects the results. For example, we can put a pigtail termination on the end of the cable and adjust the diameter of that pigtail. We can adjust the resistivity of that pigtail, We can see how that affects the results. No surprise that our nice 360-degree termination has much lower coupling than the pigtail termination. So we're able to, with a very minimal analyst time, determine the effects of whether or not we should use a pigtail. We can adjust our shielding. So there's built-in models for the presence of foils and braided shields, and we can adjust details like the strands per carrier, carriers in the cable, weave angle, or we can adjust the thickness of the foil that we use and other parameters and quickly see the effects on the induced voltage of our device. And then, of course, adding an extra shield, adding that extra layer of shielding that is foil wrapped and braided, you can see results in significant attenuation. So EMA3D cable for the ESD, forced through a cable, you can see it's a very straightforward workflow. And just for comparison, this is a benchtop test. We've got a signal generator creating a time domain pulse that flows along the shield of the cable, and it induces a voltage on the inner pin of the cable, and we're showing for the pair and the triple cable that we're able to predict the coupling through the transfer impedance of the shield. So you can be confident that your coupled voltages through shields are accurate with the EMA3D cable. Okay, next let's talk about radiated emissions. Of all the EMC tests, conducted emissions, conducted immunity, radiated emissions, radiated immunity. Radiated emissions is definitely one that's very easy to fail, and certainly one that is heavily impacted by both the cable and the enclosure itself. So many RE test failures are from the cable or the cable termination. This gives us a way to talk about how we can model this. So the first part of this, we're going to talk about modeling the PCB itself in ANSYS SIwave. SIwave is a dedicated PCB electromagnetic solver that is really purpose-built for PCB and package modeling, and it lets us model, simulate, and validate individual both high-speed data channels as well as the power in the PCB, typical of modern electronics, and we can model the near-field, far-field EMI in this case when we're using SIwave. I'm going to talk a little bit about this model. This is a non-proprietary board modeled in SIwave, and so we've captured some details of this circuit, microprocessor and DDR4 chips, and then several different signal nets that in a time domain manner are excited on this board. And then SIwave makes it very easy in the frequency domain to pull the near fields and far fields for each frequency. So in this case, what we're going to do is we're going to take the near fields from SIwave, and it's a one-click process to export these near fields. So taking a look at not just one frequency, but the max across multiple frequencies, you can see this is a true broadband characterization we're getting out of SIwave. And then we'll take those fields and drop them directly in the EMA3D cable. Again, this is a one-step process. It's one button click to import those fields. And then with the mouse, we can drag that Galileo board fields into the correct location. We can rotate it. It's very intuitive, and so we can have the emissions from the board in the correct location. What this allows us to do is use the MCAD-friendly and the cable-friendly tools in EMA3D cable. With EMA3D cable, we don't work with we can work with geometry that might be hard to work with in other tools. We can import the MCAD directly. We don't have to spend a great deal of time, or possibly not any time at all, preparing for meshing. We can just import the MCAD and click mesh. But in addition to the ease of being able to import and mesh, we also have some sub-cell modeling features that make life a lot easier for EMC engineers. For example, I'm showing here our seam impedance tool. Seam impedance is an intrinsic property of the seam. So if you know what that is for a particular style of seam, say fastener spacing, you can use that value over and over again. So EMA3D, by clicking the line and then clicking the seam impedance parameters, typing them in 3 boxes, in just a few seconds we can specify the seam impedance. And so that makes specifying models much faster. Of course, we could resolve the seam full wave in simulation with EMA3D, but when we're in a hurry, we don't have to, especially if we have knowledge of our seam impedances. And then this shows what the mesh looks like of the mechanical enclosure. In this case, it's based on the mechanical CAD, no geometry cleaning or preparation required. And again, our full workflow is in SpaceClaim, so we really can think just like we normally would in our 3D CAD environment. We don't have to spend time cleaning or preparing this model. And then we hit the simulate button, and this is what we get. We get the fields everywhere. So we've got the source from the Galileo board inside the enclosure, and that creates fields in the enclosure. And you can see very clearly this shielding of the enclosure means that the fields outside are much lower, and coupling outside goes through that seam that we specified. So we've taken an extremely complex model, and by using SIwave combined with EMA3D cable, we've been able to get it to something that's tractable in 1 day. And given the throughput that we need and the complexity that we need in EMI, EMC, that's really our target. We don't want something that's going to take us weeks or months to prepare a very complex enclosure model. We want something that we can pull in the MCAD and get reasonably accurate results as fast as possible so that we can understand our EMI, EMC vulnerabilities or risk points early in the program in a predictive way. Again, this is the same concept, just a side view. And again, you can see the SIwave field import Galileo board present there as well. It's what's creating those fields in this model. And then we can probe the fields inside the enclosure. In this case, we're at 4 millivolts per meter E field. And again, EMA3D cable statistically assesses these fields. So we're getting the max, min, and mean at each frequency inside a specified volume within the enclosure. So 4 millivolts per meter and then 0.7 millivolts per meter outside the enclosure. So we can set our viewpoint outside the enclosure wherever we want it to be, 1 meter, 3 meter away to match our radiated emissions standard. And very quickly we can have something that's predictive, and we can make some wise decisions about whether or not we're going to pass or fail our emissions limit and make changes. Those changes may be at the PCB level. Those changes may be at the enclosure or shield level for the cables, but we have a tool now that can help us be predictive and quantitative with a reasonable amount of man effort. Okay, let's talk a little bit about consumer electronics. In this case, we're looking at combining radiated emissions from, again, an SIwave field import and EMA3D cable again. Again, I've used the seam impedance tool. With one click, we define where the seam is, and we can drag and drop the SIwave fields into the location inside the phone, and then we can specify the data and charging cable. And so in EMA3D cable, we've got the ability to have multiple shield levels, branches and cables. This cable doesn't branch, but if it did, we could resolve that. We can handle foil braids, foil shields, braided shields. We can twist in the cable shields. And specifying those cables takes seconds. There's a pre-built library of standard types, or you can specify manually, but it really is as simple as just right-clicking and adding conductors or importing an export from the standard wire diagram software tools. And then, of course, in SIwave, we're able to look at a board. This board is excited, and we capture the near fields. And the near fields, again, it's just a one-click import, and with our mouse, we can drag that SIwave field box onto the correct location inside the device. and then when we let it radiate. In this case, we're going to drive two things. We have an arbitrary number of sources we can use in EMA3D cable. So we're going to let SIwave emit. We're going to actually drive the cables as well. So both are going to be operating at the same time. And you can see very clearly the SIwave fields from the PCB. You can also see the pulse coming from a square wave on the cable data port as well. So you get the combined emissions at an observation point some distance away from both. We don't have to do them one at a time. We can do both. We see the effects of the seam. We see the PCB emission effects. We see the cable emissions effects. This is the true view, just like you would have in an EMI-EMC chamber. But this is something you can put together in a day. It's not a month-long simulation effort. It's a really fast process, and new users can get to this point reasonably quickly. Okay, let's talk about some other environments. So we've covered radiated emissions. We've talked about ESD. Let's talk about EMI crosstalk, which is a really important metric for cables. So we have a noisy signal in one cable that is routed next to another wire. The victim wire may have induced voltages from being routed next to the other cable. So having a tool that can quickly assess crosstalk is important. Within our devices, we have limited real estate for routing our cables. If we just follow rules of thumb, we will specify that we need separation between wires that may be overly conservative, and that really constrains the design of small devices. So having the ability to more accurately predict crosstalk is going to allow us to have more freedom in the design of our devices. So let's take a look at this cross-section. In this case, we've got a really simple straight wire. It's a multiple shielded pairs that are themselves surrounded by an overall shield. So what we want to do is look at the coupling from one of those pairs to another conductor nearby. And EMA3D has an interesting feature. We can export the S parameter characterization for that full cable harness. So what this allows us to do is capture the parasitic capacitance, the reactive inductance of that cable, and hand it to a circuit team. And they don't necessarily need to know anything about the 3D design of the cable. All they need to know is, hey, I've dropped in this S parameter model that represents the cable harness. So this has the crosstalk built into it. This has, again, the capacitances, the inductances already built into the model. So that's a nice feature. So we can then take a look by processing those S parameters in Electronics Desktop. We can extract the cable shielding. So in this case, looking at this S parameter, we're able to see the dB shielding that we're getting from having that shield. So this is the S parameter from the shield to its interconductor. We can also do crosstalk. So let's take a look. So port 1 on conductor 1 to port 2 on conductor 2. That's letting us look at the crosstalk between two conductors in the same pair. And then we can also look at two conductors in different pairs. So conductor 1 to conductor 5. So you can see, obviously, the two conductors that are in the same pair have really immense crosstalk, but the conductors that are separated across a shield have quite a bit of isolation up to the gigahertz range, and still have pretty good shielding, 30 dB or better. And so this simulation goes very fast. It just takes minutes to set up. And next, we can start to think about how those conductor position changes can affect our crosstalk. So with a subtle change where that conductor is, we can take a look at that crosstalk and see how that's affected by the cable harness. Now, again, in this case, it's a very simple straight cable where all the conductors are in there. But we can also run this in the 3D path of the cables where the conductors are separated by some space. We have the effects of the enclosure itself. So this gives us really comprehensive platform to look at the effects. And you can see it's such a subtle change at certain frequencies gives us actually pretty big change in the isolation for these conductors. Okay, let's talk a little bit more about radiated emissions and radiated susceptibility, especially looking at subgrid modeling. So with EMA3D cable, we have the ability now with R2 to do a subgrid where we're going to have higher fidelity in certain regions of the simulation space. So we can keep our grid coarse for the enclosure, but we can have a higher resolution grid around the PCBs. So in this case, let's take a look at a computer component, and this is an enclosure. For the enclosure, we're going to use a 1.5 millimeter mesh size, and then for the subgrid, we're going to use a 0.5 millimeter for it. That'll help us be able to resolve some of the features of that PCB. So you can see the PCB in the top frame is meshed with a higher resolution mesh. The lower case would have been if we used the 1.5 millimeter mesh on that particular component. And then in this particular model, we've added our SIwave field import in the DDR, in the PCI slot, and then we've added our processor as a subgrid in EMA3D, and we're able to see the combined emissions from both. So again, we're not limited to just SIwave. We can also have directly modeled PCBs in EMA3D, and we can have an arbitrary number of sources modeled in an arbitrary number of different ways. So we can have emissions, in this case, from a cable, from a directly modeled PCB, and SIwave fields. And we get the combination of all of those sources together, and then we have the effects of the attenuation of the seam, and we can probe the field some distance away, 1 meter away, 3 meters away, whatever it is, and capture the results. So we can start to be predictive about our real EMI-EMC setup, not just our PCB, but our true metric. Okay, let's take a look at radiated immunity. So, of course, radiated immunity is the sister of radiated emissions. In this case, our antenna is producing fields external to the enclosure, and we continue operation of the unit to analyze whether or not there's upset or even in some extreme cases damage to the unit under test. So in this case, we've got external illumination. We'll use a plane wave, which is representative of EMC antennas operating in their far field. And we have a cable with a shielded twisted pair. We've got our seam, and we've got our subgrid processor in this model. So in this case, the plane wave comes in, couples in through the cable, couples through the seam, and gets into the enclosure. And so we can measure directly the fields, and then we can see the voltage that is induced on the PCB nets. And so we can compare that time domain and frequency domain induced voltage on the PCB nets to our susceptibility level to determine whether or not we've got a risk of upset or damage in this particular case. Okay, let's talk about some more exotic materials. So we can imagine that in our enclosure, we may want to include some EMI absorbing tapes. We may want some ferrous chokes. There's several different things that are frequency dependent and complex materials that will be included as part of our setups. So in R2, we've added features to resolve frequency dependent materials. So we allow users to read in an ASCII file with the permittivity and permeability of any arbitrary material at a variety of frequencies. And once we've done that, EMA3D is able to reproduce those frequency dependent effects in the time domain simulation. And in this case, we've picked just a simple coax, and this coax is loaded with, instead of a normal dielectric, we've added some magnetically lossy material. So you can imagine at low frequencies, it will act just like a regular dielectric fill, and information can flow on the coax. However, above a certain frequency, that absorber dielectric fill the magnetic losses will turn on, and we won't have any propagation above a certain frequency. So for a cross-check, we use HFSS, and we're going to compare that to EMA3D cable. So we can see for the S21, which is the coupling from one end of the coax to the other, that we see basically the same result. It's 0 dB at low frequencies, and once the absorber starts to turn on, once you get above a couple gigahertz, basically nothing is getting through down this transmission line. So it's nice to know that EMA3D, even though it is a time domain and voxel-based tool, can still handle these incredibly complex type of material properties. All right, let's talk a little bit about connector transfer impedance. EMI/EMC engineers that are worried about the performance of their shields often will use transfer impedance characterization. EMA3D cables is a great tool for both modeling the fixtures to help design a good test and also predicting the performance of a connector during that test. So let's talk about this particular model. We're going to do a measurement, a full wave simulation, and a wire harness simulation that uses the transfer impedance method. So we're going to have physically model the Cat8 connector. Now Cat8, it looks like an Ethernet cable, but it's a little bit more conductive. And so this just shows what the receptacle looks like. We've mounted it in a mill circular connector just so we can do a good measurement. And then this just shows the overall fixture. Because we're only measuring the connector and not the overall transmission line, it's much shorter. This transfer impedance fixture gets longer for looking at the overall cable shield and not just the connector. We performed a 3D full wave simulation in EMA3D of the connector itself. So again, it's partially metallized, and only where it's purple is there a seam joint where it's about 100 milliohm. And this is a rough measure. So when we measured the resistance of this connector, just wiggling the connector, it went plus or minus, but it basically settled on 100 milliohms. So not great electrical connection. One of the nice things about EMA3D cable is we can apply all of that contact resistance in this using the seam joint formalism. So this lets us just click the line, click 100, type in 100 milliohms, and we've got that extra resistance where we want it to be. And then we can run the full wave simulation, and we can compare the transfer impedance we get in the simulation to what we measure. We also modeled it another way. We used transmission line theory, or our EMA3D wire modeling tool, where we can put in a parameterization of the transmission line theory transfer impedance. And so we've taken the same length of the connector and the stub of the shield, about 6 centimeters, and we've matched it to the resistance and transfer inductance that we saw experimentally, and we're able to use that as a simplified model. The point is, we don't have to model every connector full wave. Once we have modeled it full wave once or measured it in a transfer impedance fixture, we can use that value going forward. And so that will simplify our process. Measure once or model full wave once, and then use it in transmission line theory many times. And you can see the cross comparison of the results. The blue is the full wave simulation. The red is the transmission line theory simulation. And then the yellow and green are the measurement across two bands. Now our measurement really, you start to hit resonances above 70 to 100 megahertz. So that's really where this comparison stops. The simulation, of course, can go to a much higher frequency, but our measurement just loses fidelity. Generally, we need to switch to screening attenuation for higher frequency coupling through shields. But we show that we can capture the effects of the resistance as well as the aperture coupling of that Cat8 connector. All right, let's talk a little bit more about the submodeling features in EMA3D to model PCBs. In this case, let's take a look at our new ability in R2 to model solid bodies. So our solid bodies can be the PCB mace materials or or other types of dielectrics, or really any material that we want to model as a solid body. So EMA3D, in the previous version, we had the ability to model a lot of things with surfaces and lines. Adding bodies lets us handle dielectric materials, lossy materials. Again, we have the advantage of our fast, forgiving, and efficient mesh engine that really makes short work of a very complex geometry. So we want to assign the material properties to the copper trace first. And in this case, we're using our EMA3D current source. We can apply that to the shield that is covering the PCB. And we have a ground plane that represents our enclosure. And although we don't have a direct conduction path for ESD, we know that that ESD event is going to induce voltages and currents on nets of the PCB itself. So this is our 3D mesh. We've got the copper surfaces, but we've also captured the FR4 bodies in this mesh. And then we can plot the resulting fields from the ESD event. You can see, indeed, even though we have no direct coupling path, the fields will induce currents. Okay, so let's talk about EMA3D cable's advantages. So again, EMA3D cable's a solver that has been validated for many, many decades against measurements on some extremely complex platforms. And so users can have confidence that EMA3D can solve Maxwell's equations and get results that are relevant to EMC, because that's the primary domain that it's been applied over these years. If there is a reason, if you get one thing from this webinar about EMA3D cable, it should be about the workflow. That is really the biggest difference between EMA3D cable and other tools, is just its ability to really streamline the workflow, to compress what in the past might have been a weeks or months long journey with extremely complex geometry to something you can do in a day or two with a high degree of complexity. And that we're able to do that because of the rapid and forgiving mesh engine. So it is tolerant to some very sloppy geometry, so we don't have to spend a lot of time cleaning and preparing for meshing. And we have a huge capacity. We have an arbitrary number of sources. We can have all the enclosure details, all the cables. We've had products that have had hundreds of individual cable conductors. We've had vehicles and enclosures that have hundreds, maybe thousands of individually defined surfaces within the product. And we're able to capture all of those details in the shortest period of time, both to prepare the model and then to run the simulation full wave. And again, because we're using the finite difference time domain method, this technique scales very efficiently, and it uses the standard ANSYS HPC technology to perform that scaling. Okay, so I am going to hand it back to Kaylin, and we will work through questions, as many as we have time for.
All right, thank you, Tim, for that informative webinar. And now let's get to the questions we received. So first question is from Lynn. It says, or she says, what are the limitations on cable insulator materials, dielectric only or complex magnetodielectric or lossy dielectric materials, and cable insulators layers within EMA3D cable?
Yeah, so let's talk about that. So I'm going to go back to this section that talks about the dielectric material. So in this case, EMA3D cable can pull in a true frequency-dependent material. So it can be lossy in an electric kind of way, dielectric losses. It can also be lossy in a magnetic kind of way, magnetic losses. And as long as the user has a frequency-dependent characterization of the permittivity and permeability versus frequency, then EMA3D can model that material, and it can be applied anywhere. One limitation, though, if you would like to use this needs to be applied full wave. So we can model cables full wave. We can model the cables with the wire simulation code. those losses are not in the wire simulation code, they're in the 3D model. So we need to go full wave to capture those kind of effects that we're talking about.
Okay, next question is from Alex. Can you model connectors of a cable? Often those don't have shields in the connectors, so there can be crosstalk in it.
Absolutely. So let's take a look. Again, in this case, we're directly 3D full wave modeling this connector. We have multiple wires inside, and we can capture the crosstalk between those connectors. This particular connector is partly shielded. It has some metal, but then there's actually a huge aperture. So we could, however good or bad the connector is, we can model it with this process. We can do it full wave, and further, if it's amenable to this, we can extract from our full wave simulation the transfer impedance, and then we can use that transfer impedance to characterize that connector the next time we see it, and make specifying the model something we can do much faster. So as you can see, a lot of things in the workflow are set up that way, where we can zoom in with more fidelity when we need it. When we want to zoom out a little bit, we're able to use transfer impedance of cable shields, seam impedance characterization, and other types of shortcut modeling tools that retain the accuracy but allow us to specify them in seconds. So we have multiple ways to handle the effects of that connector.
All right, next question is from John. Is there detailed documentation or manuals out there on EMA3D cable with space claim hosting so someone can quickly use the tools to model real cables, such as those with connectors that use wire pigtails for shield termination?
That is a great question. I failed to mention that in R2 release, we have hundreds of pages of documentation, and they're in the inline help. So they're context-based, so if you need help with this section of the tool you're using, you can just look for the question mark button and click it. There literally are, if it's printed out, something on the order of 300 to 400 new pages. So there's quite extensive documentation added for this R2 release.
Okay, and we have another question from John. Looking at your Cat8 connector, it appears that you modeled the wires using M-harness, segments and junctions with metal structure around it. What was the mesh size? We sent a connector file to Kellen for help as the mesh got so small we did not get the needed low frequency resolution needed for typical cable effects.
Yeah, I am trying to remember off the top of my head the exact mesh resolution, but let's see. So that connector is just maybe 8 millimeters across, and it's got 8 cells. So it's probably on the order of 1 millimeter for this cell size, but we've dialed it down certainly sub-millimeter for connectors in the past. So mesh resolution shouldn't be a particular issue. For that particular connector, I'm sure it's something we can get to the bottom of what's going on with it.
Okay, next question is from Tapesh. Can the software be used to assess shielding effectiveness of cables and connectors?
Absolutely. So in this case, I don't show it, but we can actually, instead of looking at transfer impedance, we could have done this as shielding effectiveness. One of the nice things about EMA3D cable is we have a built-in tool for shielding effectiveness that will give us the frequency-dependent shielding and a statistical assessment of an enclosure, or we can do the same thing for a cable. So yes, we're natively supporting shielding effectiveness as one of our primary outputs. And all of that data processing required to make those plots is built in. So you're just right-clicking and telling the software you want that shielding effectiveness plot.
All right, and then we have a question from David. Do you have a library of 38999 connector parameters in a library?
At this time, no. So we have a lot of shield types built into our library, both nickel copper and we've got some of the Glenair branded materials by part number. At this time, the software does not ship with connector back shell preloaded information, but that's certainly something we're always interested in adding new components to our databases. So look for that in the future, and we can certainly work with customers on a case-by-case basis to add their desired connectors.
Okay, and then we have another question. Can I reuse my enclosure and cable design for multiple environments, such as emissions and immunity?
Yes. So if we take a look back at this model before, we can see that we used the same enclosure and PCB for immunity, but we also used it for radiated emissions. So that's one of the powerful advantages of this product, is it can be used for radiated as well as conducted EMI/EMC metrics. So model reuse is one of the primary, goals for the tool, and that's part of the workflow of engineers that use EMA3D cable.
Okay, and another question. How long does it take to develop a working simulation model?
Okay, depending on the model, but with this level of complexity, you're talking about a day of work, 2 days of work. It certainly would be weeks or months effort if we were to use a method that doesn't use the voxel style mesh engine. So that's really the biggest differentiator for EMA3D cable, is the ability to work with all kinds of geometry.
All right, and our last question is, my method of compliance is test. Why would I want to do simulation?
Yeah, that's a fair information. So, fair question. So, as we mentioned in the beginning, that often that is the case, that our full unit test or our full platform test is our method of certification. But if you have a failure at that point, it is very late in your program life cycle, and it is very expensive to make changes late in your design life cycle. By having simulation that captures all aspects of your EMC design, both the electronic PCBs as well as the enclosure and cables, we can push those design changes, if they need to occur, to a less costly phase of your program. So that's the first answer. The other answer is more and more integrators of electronics are asking for simulation data. So yes, they know that the test will be the ultimate pass-fail criteria, but they're saying, let's go back a few months or maybe a year before you have to give me your test results. Show me your simulation so I know you've got a good EMI/EMC design. And so that's more and more common for tier 1 suppliers of electronics to be required by the prime to do simulation. Certainly for many integrators as well as suppliers, having a digital process for design and validation is a differentiator for those companies. So there's more and more interest in doing the full EMC workflow. It's just that up until now there hasn't been maybe the tool that fit every part of that workflow.
All right, and we received 2 more questions, or 3 more. The first one's from Tapesh. Is there any limitation in terms of the PCB file extension that is supported by software ODB++?
Yeah, so SpaceClaim has added in R1 earlier this year, started adding ECAD imports, so we can import many types of ECAD directly. For other types, you can use the electronics desktop suite to import the ECAD, which is basically handles all popular formats and export them directly into SpaceClaim. So depending on your particular workflow, there's a couple different ways you may want to work with that ECAD, but they are supported.
All right, and another question from Sophian. Generally, most of the models fail at the resonance frequencies. Could you show a comparison between the measurements and the simulation at the resonance frequency?
Yeah, that's it's a limitation. The resonance makes it hard to measure transfer impedance at the resonant point. But in some cases, we've shown some of these S-parameter characterizations where we can capture these higher order effects that are frankly kind of hard to characterize without a very good fixture. You need a nice airtight TEM cell to get to high frequencies and have good correlation. But there's nothing that limits EMA3D cable from getting to those frequencies. We can resolve them. And while the focus of today's webinar was not validation, we can, in other cases, show validation in the S12 and the shielding effectiveness at these resonant frequencies.
Okay, and our final question from Tapesh. Does any solution from EMA support CWI simulation?
I assume that's just CW simulation. So in that case, the answer is yes. There's a couple of ways you could do it. You could do it CW frequency by frequency, but the recommended way in an EMA3D time domain simulation is use a transfer function method where we can use a very short pulse in the time domain that has all the frequencies, and by careful use of transfer functions, we can extract our CW results for both susceptibility or emission. So yes, usually since we're doing EMI-EMC, we're comparing to those CW cases.
All right, it is time to conclude this session. As a reminder, any questions that we didn't get to will be addressed via email. You'll also be receiving an email from us tomorrow with a link to the recording of this presentation. If you have any questions about a particular section, please feel free to reach out through the EMA3D.com website or our email. Thank you for your time and attention, and have a great rest of your day.